Good day. Today we continue the second part of our presentation about the Kakutani Neumann transformation. As you may recall, this is a transformation defined on the unit interval. And it was defined by an inductive process called cutting and stacking. We'll recall here the definition. The process consists in constructing a sequence of columns, Cn. And you may recall that each column consists of levels or intervals, all of the same length. And the number of levels in a column is called the height. It's called h, the height h of a column C. So let's recall the construction. We have, it's by induction, so we have to first have the base step C0. We call this column C0. And we said last time that these sometimes are called towers or Rochlin towers or Rochlin columns. So C0, for the case of the Kakutani Neumann transformation, consists of the unit interval 0, half, left close, right open. Then what we do is give the inductive step of how to go from column Cn, we'll call it here Cn, to Cn plus 1. So let me just draw here. Cn consists of Hn levels, all of the same length. These are subintervals of the unit interval, and all is of the same length. Once we have a column Cn, what we have is a column map. So you'd have here any two arbitrary levels, and suppose you have a point x here in a level, you have t of x. T sub Cn, we'll write here Cn of x. And T sub Cn of x is just the point above in the level. And on each level, the column map has been defined by unique orientation preserving translation that sends that level to the next. Okay. So we have the column Cn, and it defines a column map. So to complete the inductive step, what we have to do is we have to say how we construct column Cn plus 1 from Cn. And in this particular case, that is obtained by cutting each level in Cn in half and stacking the top right on top of the left. So in Cn plus 1, here we draw the bottom of Cn, which would consist here of Hn many levels. And then we draw the top of the right of Cn, which consists of another Hn levels. And in Cn plus 1, we have a total of 2 Hn levels. We will write here Hn plus 1, the height of Cn plus 1 is 2Hn. So this completes the process, the inductive step, and defines a sequence of columns Cn, and this defines a transformation on the unit interval. One of the properties that we mentioned last time was that this transformation is measure preserving. What we're going to do now is we're going to take another look at this transformation, and now as a map of the unit interval, and where we will see again the property of measure preserving. And it helps to see how this process defines a transformations on the interval. So first what we'll do is I'm going to draw here in this part, I'm going to draw the unit interval. Okay, here's 0, 1. And we're going to define a map. So this is, it helps to illustrate, think of the unit square here. This is 0, 1. Okay. All right. Now, let's see, you may recall last time how we defined C1. C1 consists of, we cut C0 in half. So the bottom of C1 is the interval from 0 to half. The next one is from a half to 1. And C1 sends a point above it. So here, as you can see, the way this is defined is by translation. We said this last time. If you pick an x here, T of x is x plus a half. Okay. So what we're going to do is now is position this in the unit interval. So we're going to draw here 0, half, this is half. And you can see that the interval 0, half is sent to the interval half 1. So a graph, if we were to graph t here, looks like this. And we can think of it roughly, this is the square. So that's the graph of t. What we're doing here is graphing t. Now, let's continue. Now, if we look at what happens, to get C2, we cut each one in half, and this top left is going to send to the bottom right. Okay, so the interval from a half to 3/4, which would be here, half to 3/4, half to 3/4 is sent to the interval from a fourth to a half, which is here, a fourth to a half. So here, if we draw this part here, the graph of the t is this one. Okay. So that's t. Now, if we continue, as we continue the cutting and stacking process, we will see that we will see where the interval from a fourth to 7/8 goes, and that will go somewhere here. And the next interval will go here, and then to here, etc. Okay. So this defines, as we can see here, this will be a graph of the Kakutani Neumann transformation on the unit interval. Okay. So using this one could partially to give the formula of the transformation as a partially defined function in the unit interval. First, when x is between 0 and half, t of x is x plus a half. When x is between half and 3/4, t of x, in this case, we subtract minus a fourth, okay, etc. And then etc. here. All right. Now, in this graph, it helps us to see the first property we're going to remark that this transformation has, which is that of being measure preserving. So let's write that here. Okay. So t is measure preserving. So we'll write here, measure preserving is a property and this means that for all measurable sets A, the measure, which we're going to think of Lebesgue measure here, denoted by lambda, the measure of t of A is equal to the measure of A. Here, we are assuming that t of A is measurable, but that's something that we already said last time, that one can prove that t of A is measurable because it being a measurable set is in some level, and what is excuse me, if A is not in a level, it will be a countable union of pieces as a level. So it's enough to look at the case where A is in some level and t of A goes to the level above it, and it's measurable and of the same measure. Okay, and one can observe that here also. All right, so now we are going to talk about the next property, which is very important, and we will give an argument for it, which is that t is ergodic. So we're going to talk about the ergodicity property. Okay. An ergodic, you may recall, we're going to give two equivalent definitions. Means that if A is an invariant set, if t of A is equal to A, if A is an invariant set of t, then the measure of A is 0 or the measure of A complement is 0. Here we are also assuming a property that t is invertible except for a set of measure 0, which we defined last time, and the viewer is invited to calculate to really see what outside a set of measure 0, t is really an invertible map on the unit interval. So we can talk about the forward image. So for invertible maps, an invariant set is characterized by saying that t of A equals to A. And ergodic means that if A is an invariant set, then the measure of A has to be 0 on the measure of A complement 0. Okay? So this means, in particular, another equivalent characterization, that if we have any two sets of positive measure, if the measure of A is positive and the measure of B is positive, then there exists then there exists an integer n such that the measure of Tna intersect B is positive. Okay. That's a property that now we are going to verify, okay, for our transformation. And the equivalence of these two properties we probably have seen in a discussion, earlier discussion, or again, the viewer is invited to verify, and it's a complicated verification. It follows from the fact that giving any set A of positive measure, look at the union over all, giving any set of positive measure, the union of T to the n of A over all n in Z is always an invariant set. Is equal to itself. Is equal to the union of T to the n of A, n in Z. Okay. Using the idea, we can verify that these two properties are equivalent. So to end our presentation of the properties of the Kakutani for Neumann transformation, we will prove that this transformation is ergodic. Okay. So we will verify this the second property. Take any two measurable sets, and we will show that there's an integer n so that the measure of T to the n A intersect B is positive. All right. So let the measure of A be positive and the measure of B be positive. Okay. So the first important argument we're going to make here that follows from the construction is that there has to exist a level that is very full of A and a level that is very full of B. Okay. So we will say, and we will write this here, I is at least 1/2 full of A means that the measure of A intersect I is bigger than a half measure of I. Okay. So the part that A occupies in I is more than half of the measure of I. Because the levels generate the measurable sets, the levels in the columns, because it's a refining, one can verify that giving any set of positive measure, there has to be a level that is at least half full of A. We could find a level that is at least 1/4. We will see for the argument that we're going to do here, it's enough to say that it's a level at least a half full. Okay. So there has to be a level that is half full of A. There has to be a level that is half full of B. Those levels may be in different columns, but we make an important observation that if we find a level that is at least half full of A in a column Cn, in Cn, when you cut this in half, at least one of those halves must continue being at least half full of A. So in Cn plus 1, there must be a level that is at least half full of A. Using that idea, we're going to write this property. Then there exists an n, so that in Cn, there's a column Cn where we have the following picture, where there will be a level that is at least half full of A, and we're going to think of A here as this color, this is A, and there will be a level that is at least half full of B, which we're going to think of B as red. Okay. Now, so the first argument what we are using here is that we can find a single column where there are levels that are both at least half full of A and B respectively. Okay. So this follows from the measured theoretic properties of the, and this is an important part on the columns. So we can find a single column. Now we don't know where those levels are. It may be that A is above B, like here, or it may be that A is below B, or it may be that A is in the same level of B. In this case, we don't know, right? We could, if we wanted, we could do more, but we will see that in this case, it's not necessary. So from this picture, we already see that there has to be an integer n so that T to the n of A intersects B. So in this case, if we move A down, note that n is an integer. It doesn't have to be positive or non-zero. So there will be t to the n of a. So t to the n of a, because t is a translation on levels here, t to the n of a must have more than half the measure of this level. B has more than half the measure of that level. So there must be an intersection. It must be the case that the measure of t to the n of a intersect b is positive. Okay. So that ends the proof of ergodicity. So let me just go over this idea and a couple of things. First, we have used some measure theoretic properties, which are that we have used the fact that the levels form what I like to call a sufficient semi-ring. So the levels generate the measurable sets, and because of that, one can approximate measurable sets by finding a union of levels, and the consequence of that is that one can always find, for any measurable set of positive measure, we can find a level that is very full of that set. Okay? So we have used that fact, and that's an important fact from measure theory that the viewer is invited to verify. Then the next fact that we have used is that we can actually find level, given A and B of positive measure, we can find a column where there are levels that are full of A and B respectively, and those are in the same column. And for that, we use the fact that if we find a column where there's a level that is more than half full of A, when you cut that in half, at least one of the two must be more than half full of A. So Cn plus 1 will have one level that is at least half full of A, Cn plus 2 will have one, etc. So if, for example, you find a level for A in column C100 that is at least half full of A, and for B a level in column C200 that is at least half full of A, you can stay in C200 and move the A to C101, C102, etc. You will continue, and eventually you get to C200 and you see sub 200, and you will find a level that is at least half full of A. So you can put both levels that are full of A, more than half full of, at least half full of A and B respectively, in the same column. We have used that argument. Once you have it in the same column, then it's easy to see. You just move one, move A. As you move, you can move A up and down, and you can see they will cover all the levels. And as you move up and down, A is covering more than half of this level. So as you move it up, the image of A will cover more than half of that level above, more than half of the level above, and there will be an intersection. So that's the end of the proof. Let me leave the viewer here with two questions. It's very interesting here. In this case, this argument doesn't show that n is different from 0 or that n is positive. So a similar argument can be used, we can refine this, so I'm leaving the reading for to actually prove that you can choose for any A and B, you can always find an n that is positive. It's possible. One can show that. So with that question and the presentation of the Kakutani polynomial transformation that we've shown is transformation of the unit interval, and we've shown too its basic properties, that being measure preserving and ergodic. So we end our presentation.